Good morning, everyone. My name is Valeriia Starovoitova, and I'm working at the International Atomic Energy Agency as a Radiation Technology Coordination Officer. Today, we'll be talking about accelerator technologies and various IAEA activities to promote them. I'm going to talk primarily about different ways to replace cesium-137 and cobalt-60, which are the two most commonly used radioisotopes in different applications. These particular isotopes, due to their relatively long half-life years, are used very, very broadly. For example, they're used in medicine for therapy, for blood irradiation to irradiate tissues. They're used in food and agricultural applications, specifically for sterile insect technique and for food irradiation. They're also used very widely in industrial applications for sterilization of medical devices or cosmetics, for cross-linking of various polymers, for non-destructive testing to study defects of different structures. And of course, they're used very widely in different R&D studies for biology, geology, material science, chemistry, etc., to support all the applications that I just mentioned. Due to the high diversity of applications, various irradiators, cesium and cobalt irradiators, exist, and they differ by the activity of the source, by the geometry, and by some other parameters as well. Therefore, if we want to replace these irradiators, we also need to think about what kind of accelerator is suitable to replace a particular cesium or cobalt irradiator. So now I'm going to talk about three specific cases, considering three different irradiators, one cesium and two cobalt, of various activities used for different purposes. And I'm going to show you what kind of accelerators can be used to replace them. Some of these machines already exist, some are still under development, but nevertheless, I think it's important to look into specific cases. And the very first case I'm going to talk about is cesium blood irradiator. So typically it's a relatively small machine, a relatively low activity. The typical cesium blood irradiator is 1 to 10 kilocurie, and there are thousands of them installed worldwide. Primarily, they are used for blood irradiation. However, at the same time, they can be used for some R&D activities. And nowadays, in different countries, owners of these machines are motivated to replace them, to change them to accelerators by regulatory, financial, and operational considerations. Several machines from various vendors are already available to replace them, and there are several programs ongoing in different countries where accelerators are already replacing cesium blood irradiators. In the table on this slide, you can see some parameters of the already existing machines to replace cesium blood irradiator and the next generation accelerators, which can be suitable for both blood irradiation and R&D purposes. For example, you can see that currently existing machines have relatively low energy. They have about less than 1 MeV. At the same time, relatively high current, providing suitable dose rate. The next generation of accelerators can be of higher energy, but slightly lower current to provide comparable or even higher dose rate. You can also see that the size and the weight of the unit can be comparable, the power requirements, and approximate cost and the lifetime. I would like to add also that these numbers, as well as the numbers you're going to see on the next slide, are coming from the consultancy meeting that was conducted here at the IAEA. Several experts came to Vienna in 2019 and prepared a very thorough document that summarizes different accelerators and different ways to replace cesium and cobalt machines. And I will share the document with everyone. You can find a lot of useful information there. But anyway, the takeaway point from this slide is that machines already exist to replace cesium blood irradiators. However, there is always an option to improve, and we hope that several companies which are manufacturing accelerators will continue working on it and develop nice machines. The second case I would like to talk about is a cobalt research irradiator. And cobalt research irradiator, cell-shielded cobalt irradiator, such as the one shown here on the figure, gamma cell 220. There are many of them installed worldwide. They are of higher activity than cesium blood irradiators, typically tens to hundreds of kilocurie. And some of these facilities consist of not just a small unit, but they also have a concrete bunker with either a source pool or a source rack that can accommodate large volume of samples. Mostly these irradiators are used for R&D purposes, and most of them are located in universities. However, for many facilities or many universities, they also use these irradiators for small-scale industrial applications. You can see a table which is very similar to the previous one. Again, it talks about different parameters of the accelerators that can be used to replace such a source. And as you can see, the energy now is higher. We're talking about 4 MeV, and we're talking about two different currents to replace small irradiators, self-shielded as shown on the figure, and also large irradiators such as irradiators with bunker and a source rack or a source pool. Again, depending on the irradiator you want to replace, of course you will have to have slightly different accelerators at the end. And again, there are some parameters here that tell you approximately what kind of machine and what kind of costs are you looking at to replace this unit. Finally, I would like to talk about industrial irradiators, high activity cobalt industrial irradiators that can have megacurie quantities of cobalt. And currently there are 500 megacurie of cobalt used worldwide for either food irradiation, that's typically true for lower activity facilities, or sterilization of medical devices, which is typically done at high activity facilities, order of 5 megacurie or so. Table at the bottom again summarizes the parameters of the accelerators that would be necessary to replace 1 megacurie or 5 megacurie cobalt source. You can see that energy is much higher here. We're talking about 5 to 10 MeV. Current is also rather high, and of course the cost of the accelerators and the overall facility is significant. What's interesting here is that you can see two modes. You can see both X-ray and E-beam mode to replace either 1 megacurie or 5 megacurie sources. And for different modes, you have different energies and different currents. And you have these two modalities now because different products can be irradiated with in different way. For lower density products, E-beam would be beneficial. For high density, X-ray would be beneficial. Also, there are different regulations for different materials depending on X-ray or E-beam modality. Anyway, it is obviously much more complicated and much more costly to replace higher activity sources compared to the lower one. The machines are more expensive and more complicated. The facility is much more complicated and expensive as well. However, there are several companies that are working on the high activity, on the high energy, high power machines. And there is a lot of work done recently to make these accelerators available, to make them reliable. And some of these machines are already operational, and we hope to see scaling up in the very near future. To summarize everything I have shown so far, I prepared several bullet points. And I would like to start with acknowledging that what I hope we all agree, that accelerators provide a very nice alternative that addresses one of the challenges posed by radioisotopes, namely that accelerators have a much lower risk profile. And it's true that accelerator technology is mature enough to provide solutions for some applications of cesium and cobalt. And that's especially true for the low energy commercial radiation equipment market. The high energy and high power irradiation equipment market has unfortunately expectations that cannot be fully met at this time. And we're talking about a combination of price, operating costs, and simplicity of the equipment. However, continuous improvement of accelerators and subsystems can make these accelerator-based solutions more attractive. To meet the expectations of customers regarding reliability for isotope sources, we need to continue improving reliability and electrical efficiency of the accelerators, and more R&D is necessary to do it. Now I would like to switch the gears a little bit and talk about different activities that IAEA is conducting to support accelerator-based technology. Here you can see a flow chart, an org chart showing different departments, and specifically Department of Nuclear Science and Applications, where I belong. And under this department, there are several divisions, and Division of Physical and Chemical Sciences it deals with radioisotope production and radiation technology. And this is the section where I work at. And our section is involved in numerous coordinated research projects, in technical cooperation projects, and also conducts regular activities such as publications, meetings and conferences, working with collaborating centers, organizing expert missions, and so on and so forth. Our activities are focused in different areas, and I would like to specifically mention radiation technologies for environmental applications, radiation technologies for material modification, radiation technologies for cultural heritage, and alternative radiation technologies. These are the areas that deal with both high activity sources for all these applications and also accelerators. So for either of the applications, be it environmental, material modification, or cultural heritage, we always consider both isotopic sources, but also non-isotopic sources, alternative technologies. One particular activity I would like to talk about today is the database on industrial irradiation facilities, DIIF. This portal was created on the Nucleus platform, and you can see some screenshots here, and it contains information on numerous gamma, E-beam, and X-ray industrial facilities. You can see a map here and different pins, and basically each pin corresponds to a facility, and it's interactive. You can click on it and you can see the name of the facility, location, and some information of what kind of products are processed and how and so far. There is also some information on alternative technologies in this profile, and there are a lot of relevant activities such as coordinated research projects, publications, meetings, some information on upcoming events, conferences, schools, training, and so on and so forth. For example, as I mentioned earlier, all the numbers in the tables come from the meeting which was conducted in 2019. The report of this meeting can be found if you go on this website. It can be found on the portal together with all other relevant reports and publications. So I encourage everyone to visit this webpage and to check out the DIIF portal, and I'm sure you will find a lot of interesting information there. We conduct a lot of various coordinated research projects, and I would like just very briefly talk about each of them. We have a project which is focused on radiation inactivation of biohazards using high power electron beam accelerators. We have another environmental project which is focused on treatment of emerging organic pollutants. And a very new project which just launched is radiation effects on polymer materials commonly used in medical devices. The overall objective of this project is to better understand radiation effects on polymer materials by comparing gamma, E-beam, and X-ray radiation. And the call for proposals is still open, and I encourage everyone to read the CRP and to see if your group is eligible for that. Please apply, because the call for proposals is still open, and we are looking for some good research groups and some good experimental and computational work in this area. We also have some other CRPs. I'm not going to talk about all of them, but please read the titles and please find this information on the IAEA website. Again, if you think this is suitable for your research group, please contact us and we'll be happy to answer all your questions. Our section participates in a lot of training opportunities. Specifically, I would like to mention two of them. One is a World Nuclear University School on Radiation Technologies, which is a 2-week program happening every 2 years. The latest one is supposed to happen in October 2021 in South Africa, and please check out the WNU website for more information and some updates. I would also like to mention the joint Rosatom IAEA School on On-Power Nuclear Applications. This is a 1-week program which will hopefully happen in June 2021 in St. Petersburg in Russia. So again, please check the DIIF website. More information will be posted there. Finally, I would like to talk about conferences. We have 3 conferences planned for 2021 and 2022. One of them will be in the United States of America. That will be the 14th International Conference on Nuclear Applications of Accelerators. Another one will be ICARST 2022, a meeting on accelerators for research and sustainable development. Most likely it will be in May 2022. We are finalizing the dates now. And ICARST 2022, that's the 2nd International Conference on Applications of Radiation Science and Technology, which will take place in fall 2022, most likely end of August, but again, the dates are currently being finalized. I will keep everyone posted. But anyway, I think these 3 meetings very well reflect our section involvement in accelerator research, accelerator development, and uses of accelerators. So I encourage all of you to consider these conferences and to possibly attend and share your work. This is all I wanted to talk about, and I would like to thank you for your attention. And we'll be happy to answer any questions and hope to see you soon in person. Bye bye.